Okay. So Malima will go first.
Hello, I am Shamulima, and today I will give you a short summary on the paper of galactic control in uh, NGC 3627 caused by dwarf galaxy candidate or massive black hole flyaway. So let's first get to know what the authors are discussing in this paper. In this paper, the authors investigate the organization of gas within galaxies, where it is generally flows along spiral arms shaped by gravity and density waves. In this paper, the authors highlight a particularly unusual feature, molecular constraint, which are long, narrow, and straight gas structures. These structures are uncommon because they cannot be formed through typical galactic processes or turbulence. The proposed mechanism is that these contrails may appear when a massive object such as black hole, cluster, or dwarf galaxy passes through the disk and gravitationally pulls the gas. Starting with the abstract, the authors report the discovery of a kiloparsec scale molecular contrails in NGC 3627. The structure is over 8 kiloparsec long, approximately around 200 parsec wide, with an aspect ratio exceeding 40. Observed in both mid-infrared dust emission by JWST and CO21 molecular gas by ALMA. They note that the contrails is much larger than any other similar structure known in the Milky Way that exhibits supersonic turbulence uh, with velocity dispersion uh, around 10 kilometer per second, indicating a highly dynamic feature. Moving on to figure 1. Yes. Yeah, the Wi-Fi is that room 529.
No, use 521.
521.
Yeah.
Here's 521.
Yeah.
This one.
Yes. This will be
Okay, sorry for the delay. So moving on to the figure 1. Figure 1 shows the ALMA CO2-1 data with Coulomb density. On the left side panel, it shows the signal to noise ratio for CO2-1. High SNR ratio means we can clearly detect the molecular gas. On the right panel, it shows Coulomb distribution. So this panel tells us where the dense molecular gas is located in NGC 3627. Now, moving on to figure 2. Here on figure 2, the left panel shows the WST infrared dust emission. The contrail is marked by the white arrows. The dust is glowing in the mid-infrared light. The straight narrow structure is, you can see it's very clear here. And on the right panel, it shows ALMA CO2 gas emission. The same contrail is detected in the molecular gas. This shows that the structure is not just a dust, not just dust, but it also contains dense gas. And the small sub-panel, it shows the PV diagram. This is the velocity map along the length of the contrail. The speed of the velocity is corresponding to turbulence. The paper measures this as around 10 kilometer per second, which is supersonic. Now, the authors analyzed the velocity structure of the contrails and compare it with nearby spiral arm. To get to know this better, let's move to figure 3. Here in figure 3, in the left panel, it shows a CO intensity map. This panel outlines the spiral arms, structure, extended contrails, and the main contrail. On the right-hand side, the top panel, it shows the spiral arm, shows the structure of shows the spiral arms, steeps, shows the structure of the spiral arm. It has a steep slope, which is approximately around 30 kilometer per second per kilo per sec. This is normal because the spiral arm, the galaxy follows the galaxy rotation. At the bottom, the right-hand side shows the extended contrail region. It is also very steep. It has same gradient around 30 kilometer per second per kilo per sec. So this part is also rotating with the galaxy. And the left-hand side, it shows the main contrail. But this contrail has very flat line slope, which is approximately around 10 kilometer per second per kilo per sec. This shows that it is not following the normal galactic rotation. Now, regarding the formation, the authors proposed that a massive object passed through the disk, compressing the H1 gas around which is around 8,000 Kelvin. The compression caused rapid cooling, transforming the warm gas into dense molecular gas and forming the contrail. The major turbulence is around 10 km per second, exceeding H1 sound speed, supporting shock-driven cooling mechanism. Now, using the width control with around 200 per sec and velocity dispersion around 10 km per second, the authors calculate the crossing time, which is around 20 million years, which indicates that the contrail was formed not long ago. For the contrail to remain narrow, the flyby speed must satisfy around 300 km per second. The speed, this speed is faster than the galactic timescale, which is around 100 million years, explaining why the contrail must have survived. Applying the gravitational wave theory, the authors estimate the mass to be around 10 to the power 7 solar mass. So to conclude this paper, the The authors conclude this paper as that the perturber's mass is around 10 to the power 7 solar mass, which is consistent with either a massive black hole or a dwarf galaxy. They emphasize that the galactic contrails are very valuable tracers for massive dark objects, offering a method to detect otherwise invisible perturbers in the galaxy. They also suggest that the future surveys such as Rubin LSST could search for stellar counterparts, while other higher resolution ALMA observations could reveal the additional kinematic features of the perturbers. That would be all.
Okay, thank you for the summary. Any questions, comments?
Okay. Thank you.
Can you explain again how this contrail is different from like a spiral arm?
Here, this is the spiral arm.
Okay.
And this in the middle, the red dotted thing, line, this is the contrail. Here, I think they have said it's like easier to see, but I cannot see properly. But they have like showed the arrow. This is the contrail. This is the length of the contrail.
Okay.
Is there a similar thing here or not here? Here?
I'm not sure because they haven't mentioned that part. They have just mentioned this one.
I
Thank
have
you.
also a question.
Oh.
Sorry, Angel, did you finish?
Yeah, I think I finished. Thank you.
Okay, sorry. Thank you very much. I have a question. So I think this is interesting. Then I wonder, say this is this kind of trajectory of a moving object? Say either black hole or dwarf galaxy is moving straight. That's why we see straight line. Then I wonder if that's the case, then is this gravitationally bounded in this galaxy, or actually this reach the escape velocity? Because if it's gravitationally bounded, I imagine that trajectory should curve because of gravitational potential. I don't really expect it to really go straight because it should curve, right? Bounded. But this looks like a very straight. So therefore, I wonder this is actually escape velocity or something like that, going so fast.
Yeah, this mention it is because of like the structure, like the black hole or the dwarf, the core of the dwarf, it is moving fast. That's why it formed. But I'm not sure why it's like straight. But here it have different like the arm. It also has the arm like main part and also the extended part. It says, but it hasn't mentioned like why it's straight or.
Yeah, because while it is passing through the center of galaxies, it should curve, no?
Yeah.
Unless it is super
So,
fast.
like it moves so fast, like it didn't get a here. It says the time period. It did not move according. Like, it's differential. It did not move like according to the galaxy's rotation.
But this I really don't know. This 300 kilometer per second sounds like consistent with rotational velocity or typical rotational velocity. So I wonder if this is gravitation bounded or not. And also, do they discuss which direction is it moving?
No, not anything.
No. Oh, okay. Yeah, I wonder if age of molecular gas may be slightly different along this line. Okay, anyway, thank you for interesting paper.
Thank you.
Our contrails like usual features of spiral galaxies.
They say it's not usual. They just mention it. How did they mention it? It's like particularly unusual feature. They say.
Okay. So did they mention like how did they choose this particular galaxy? Like, how did they know that there's something?
This was first observed by, I think, JWST or ALMA. They observed it first, then after observation, they
Followed.
followed.
Okay. Thank you.
I wish they show the simulation, then it would be more.
Oh,
obvious.
yes.
Okay, any other discussion? If no, thank you, Sam Malima, and let's move on to Tomoki.
Okay. I think you can see my screen.
Yes.
Today, I'd like to introduce this interesting GRB. GRBs. This is the longest gamma ray burst ever seen, and its duration is about this second. Before going to detail, this figure shows the typical distribution of shows the distribution of time duration of gamma ray burst. And there is two big, short one and long one. And even long one, typical duration is about 100, between 10 to 100 seconds. But this GRB continues about 25,000 seconds. So it's much longer than these typical ones. And in addition to this long duration, they show sub-second variabilities. And it means that the emitter should be some compact object. And this is maybe it is 2 points interesting point of this GRBs. Okay, they combine the data of 4 satellites, LMGBM and Cornus Wind and SwiftBat and Astroph 5, and this one and Maxi, and they make a light curve of this GRB, and maybe it starts from something like here and continues about about this time scale, and different curve shows different satellites, this one or this one or this one, and in some time they cannot detect GRBs. For example, in case of SwiftBat, they detect GRB at this time and this time, but cannot detect in this time. I'm not sure whether this is due to the variability of GRB or due to problem in satellite. But anyway, they find this kind of very long GRB with some kind of flares shown here, shown like this, maybe here. This is long time scale version. This is short time scale version. And they show some detailed analysis of this GRB. And this figure shows the relation between duration and E peak. E peak is the peak energy of their spectrum. And here is typical long GRBs, and here is so-called ultra-long GRBs. They show typically about 1,000. Sorry, they show the duration of about 1,000 seconds. But this GRB is much longer than this guy's, and E peak is a bit higher. Although they show very long time scale, its variability time scale is
very small. It is about 1 second. So it shows 1 second variability and very long duration. This is important point of this guys. And for this kind of very long this kind of transient with very long duration, one possible scenario is some kind of jetted TDE. But in jetted TDE case, the minimum variability time scale should be much longer than this value. So this minimum variability time scale is usually determined by the object size divided by light speed of light. And when this is when the system is relativistically moving, some relativistic correlation occurs. But this time, in this way, this time scale can put some constraint on the size of system, and they conclude that this variability time scale is inconsistent with jetted TDE. So they not conclude. They say that this GRB comes from some compact system, and maybe similar to typical GRBs. This figure shows EISO and redshift and such kind of things. Nothing special here, but this is a bit shows some different point of these GRBs. This figure shows the Amati relation and Ionnet correlation. It is known that typical GRBs rides on these relations, here or here. And this relation is determined by E peak and E ice, or L ice and E peak. And as you can see in Amati relation, this GRB is within typical GRBs. But in case of but for Ionnet correlation, it is a bit outside of these typical GRB populations. But maybe this is due to its long duration. So if we fix energy when we consider long duration GRB, luminosity should be small. Maybe I think it may be difficult to satisfy both of these relations for this kind of abnormal GRBs. Okay. Okay, and this is what they observe, and they put some constraint on the progenitor, and they consider what is the possible progenitor in this paper. And in addition to this light curve, they find possible gamma ray burst related to this guys. Using Einstein proof, they report a detection from stacked observations on July 1st. So if this gamma ray flow observed by, Einstein proof is a part of this DRB, the duration should be something like this. And we need some delay between start of GRB and peak of GRBs. And they also consider bulk Lorentz factor, so minimum bulk Lorentz factor using opacity argument. And they conclude that this is the possible minimum bulk Lorentz factor. And I think this is not special values, relatively small, but so not so abnormal, I think. And from the variability time scale, something like this. Sorry, from the variability time scale, we can put constraint on the size of progenitors. And using this kind of relation, they conclude that we favor stellar mass central engine. So they conclude that stellar mass central engine is preferred for this event. And here they exclude some possible progenitors, something like X-ray binaries or TDEs or IMBH case, IMBH or something like this. And I don't read the detail of this part, but they consider that this GRB may come from helium star mergers. I think because in order to make long duration jet, they need maybe big disk or something that have rapid spin. And this kind of rapid spin may be made by mergers of helium star and black hole binary or such kind of things. And this table is maybe also useful because they consider, they show they compare these values for typical transient and these GRBs. And sorry, I did not read the detail of this part, but they conduct some calculation using this helium star merger model. And sorry, I will skip detail of this part. But anyway, this kind of high rapid spinning progenitor is needed in rapid spinning progenitor may be needed for this kind of transient. If we follow their argument. Okay, maybe that's all from this paper. Maybe I missed some parts, so if we check this paper in detail, we can find some interesting point in addition to this. And there is already some papers, some possible scenario papers regarding this GRBs. Okay, that's all from me.
Thank you. Any questions?
So, in the light curve, there seems to be several bursts.
Yes.
What's the physical explanation for these big ones?
Sorry, I cannot check that point.
Okay.
And their figure don't show that kind of some periodic activities. Maybe something like here, we cannot find some that kind of variabilities. So it may be due. Okay, sorry, I cannot find that answer.
Okay.
Any other questions?
Can I ask a question?
Yes.
Okay. What is the variability time scale on figure 2? Yeah. This figure. Yeah.
Okay. Variability time scale is defined by the variability of light curves. For example, from here to here, the light curve suddenly changes. And the variability time scale is the typical time scale of this. Sorry, minimum time scale of this kind of sudden increase or sudden decrease.
So it's the changes of like all three of the color lines, or
Sorry, could you say again?
I just wonder, like you said the variability time scale is the changes of the color line, right?
Yes.
So I question that if it is the, let's say, the difference of two color line or three color line.
No. Difference in one color line. In one color line, the gamma ray count, this axis shows count, and this count change depending on time.
Okay. Oh, I see. Thank you.
Tomoki-san, so I have also a question.
Hi.
This is very different from ordinary long gamma ray burst. So therefore, progenitor should be different from normal long gamma ray burst.
They say so.
Okay.
And they prefer this helium star merger scenario.
Okay.
Maybe not just collapse, but kind of mergers of black hole and helium star.
So therefore, if that's the case, maybe comparison in the Amati relation may not be really make sense. We are comparing two different things in the same figure.
Yes, but
just for comparison, we can compare, but then actually we are comparing two different progenitors, maybe.
Yes, yes, I think so.
Okay.
So you mean this is
say we do see offset. So for example, in light panel, we see the offset of this gamma ray burst from other gamma ray burst. But then it's maybe natural if progenitor is different.
Yes, if we believe this scenario or other possible scenarios.
Okay.
I have a question. Do they report some kind of difference in host galaxy property or the location inside host galaxy?
Maybe no. I saw that they are in star forming region.
Okay, so very typical long journey.
Yeah.
Shotaro-san, actually, I read the abstract of that paper, and then I think host galaxy is also very special. They say very massive dusty stormy galaxy.
Massive dusty.
Usually, gamma ray burst doesn't happen in that kind of type of galaxy.
Okay. Maybe this is more interesting.
I can put a link to that.
Thank you very much. I missed that point.
This one.
Thanks.
So this is different paper?
Different paper, yes.
Okay.
Another paper reporting host galaxy.
Thank you very much.
I think this galaxy population is rare for long gamma ray burst.
So they say this is 1,000 times rarer object.
Maybe here. Thank you very much for information. I missed this paper.
Time limit, we should move on to Tomo-san presentation.
Okay. Okay, I want to share this paper. This is an uncovered diversity spectroscopy of 3 cold brown dwarfs obviously in an uncovered field. So they present 3 spectrum. So it's interesting that one of them is selected as brown dwarfs as a brown dwarf by Nonino et al. Paper in a color selection like our previous paper. And then 2 other were selected as AGN, but then when they put the slit on and took the spectra, it turned out to be brown dwarfs. So let's look at this spectrum. It's here. Here. So these are brown dwarf 1 to 3. And as you can see, this is a weird spectrum, right? So many absorption features from molecules because they are very low temperature. So you see ammonia CH4, water H2O, and then this pH3, this phosphine is also there. So that's very interesting. There are a lot of molecules. They can exist because temperature from the best fit model is very low. What was the temperature? I think temperature is here. 1300, 1000, and then this third one is only 550. This is only a little bit warmer than Jupiter. So that's why these molecules can survive because temperature is very low. In the atmosphere of the sun, of course, these molecules are destroyed because sun is 6,000 degrees, right? Then, yeah, so how they fit the model? They fit the model here. Then this is the left side is fitting the library to determine the time. So these are T dwarf, T1.0. This is T6. This is T8. So these are brown dwarfs. Then on the right side, they fit the model. So these blue ones are models. And then there are a bunch of brown dwarf models, SED models, but this model called the low Z fits best in all these 3 cases. And then that's where they got the temperature, this 1550. Okay. Then what should I do? Yeah, and then phosphine is here in this 4 micron region, and then this it's a little bit tricky because CO2 is here, then near the phosphine, wavelength is overlapping. So if you remember, people discovered phosphine in Venus, and that was a big news. But then later they argued it may be CO2. But in this case, the wavelength, the model fits wavelength this absorption is a little bit extended towards shorter wavelengths, and then they say they are sure that the model fits phosphine better. Okay, then once they fit the SED, they can just estimate the distance, and then some other properties which are here. So distance is 4 kiloparsec, 2 kiloparsec, and 1 kiloparsec. So they put this in this thick disk, most of them. So these 2 more distant ones are probably in a thick disk, and then this 1 kiloparsec may be in thin disk. And the metallicity is also low. You can see this is -1, and then this is -0.5. So this is a metal poor drone dose. So these are all from the models. Okay, I think that's all. Yeah, I think that's a major discovery here. So basically, they are reporting this result from this spectroscopy from this uncover. It's a sort of, you know, they're in good situation. Like when they discovered, after they discovered this brown dwarf, they already have approved the spectroscopy program of this multi-slit spectroscopy, so they can just include these targets into their spectroscopy, and then they took this spectrum. So it's nice.
Yeah.
Tomo-san, I have a question. So,
Yes.
do they have color selection before conducting spectroscopic observation?
Yes. So the one of them, I think, BD3 was selected by Nonino.
That's color selection. Okay.
Yeah, color selection. The other two are also probably color selected to be AGM, so that's why they targeted. But it turned out to be brown dwarfs.
Turned out to be brown dwarf. What I wanted to ask is a kind of success rate. If you do color selection, then how many of them are confirmed and how many of them are not? Do they discuss these kind of things?
I think this Nonino only presented one candidate, and then they did the spectroscopy, and then it turned out to be a brown dwarf.
Okay.
So it's,
I see. For that part, success rate of 100%.
Right.
Very nice. I see. Yeah, I was wondering, say, Tomo-san has multiple candidates right now.
Right.
Therefore, given this success rate, then it will be very convincing.
Yes, true.
Success
That's
rate
true.
100%.
But it may be, in my case, it may not be 100%.
Yeah, well, seems to be good news.
But our candidates include the even metal poorer ones, so I think it's interesting. Okay, if no question, thank you, Jerry.
So thank you, Tomo-san, and let's decide who will present the paper tomorrow. So Darian register, right? So we need 2 more volunteers.
So who's on Thursday again?
Stephanie, Ryan, Dora, and Darian. Nguyen, Chongqing. So Ryan, do you have any paper? Thank you, Tetsuya-san. Okay, Ancho. So Tetsuya-san. Ancho. So tomorrow we have Tetsuya-san, Ancho, and Darian. So thank you everyone for joining today, and see you tomorrow.
Thank you. Bye bye.
Thank you.